Okay, I've got 8:30, so let's go ahead and get started. Um, so let's start with this warm-up question. Looking at 7500, we want to know how many divisors it has. First thing we want to do is get a prime factorization for 7500. Factoring in general, pretty hard, although in this case, not so bad. We can say that 7500 is 75 times 100. Those aren't prime numbers, but we can keep going. 75 is 3 times 25. And 100 is 4 times 25. Or 25 times 4, I guess, because that's what I wrote. And each one of these is really easy to get a prime factorization for. So 4 is 2 squared. And then times 3. And then 25, each one of these 25s is a 5 squared, giving me a total of 4 copies of 5. So I've done my fundamental theorem of arithmetic. I've factored my 7500 down into prime factors. And then last time we talked about a strategy to count the number of divisors given a prime factorization. We've got 2 to the power of 2, so we do 2 plus 1. 3 to the power of 1, so 1 plus 1. And 5 to the power of 4, so 4 plus 1. We're going to multiply all those together. 3 times 2 times 5 gives us 30. So 30 different numbers that divide 7500. And if we wanted to list them, we could start looking at different combinations of these factors. So 1, 2, 3, 5, 6, 10, 15, 25, 12. Missed some in there, but you get the idea. Okay. Questions about that warm-up? Hopefully all coming back to you from Tuesday. So I want to ask, where does this rule come from? Why is this the number of divisors? Why does the number of divisors relate to the powers on this exponent? Yeah, so the fundamental theorem of arithmetic definitely comes into it, because we know any divisor has a prime factorization, and if it's a divisor, the primes have to match the primes from the number we're trying to divide, or be a subset of them. But why is this the formula? Why does this count? How many? Yeah, we've got some sort of combination, some sort of counting thing going on. The actual idea I want to get at is that what we're using here is something called the rule of product. So ROP in the notes. So the rule of product says, if you want to know how many ways there are to do something, if you can break that thing up into a sequence of choices, and you know how many options there are per choice, then you can multiply those numbers together, and that gives you the total number of options. So in order to count the number of something that can be generated through a process of steps, and this part is important. It's not that you have to have the same options at every step. It's that the number of options at every step has to stay the same. The number of options at each step is the same, regardless of previous choices. So in order to count the number of something that can be generated through a process of steps, the number of options at each step doesn't matter what comes before. Maybe the actual options do, but the number of options doesn't matter on what comes before. You just have to multiply the number of options at each step. Okay. Related to mutual exclusivity, different enough that I don't want to get into it right now. Let's say that. Okay, let's do an example. I want to give you a warning. I wrote this lecture a little while ago, and when I wrote it, I was really hungry. There's a lot of examples in today's lecture, and like half of them have to do with food. So if you skip breakfast, I'm sorry. Okay, so if you are at a restaurant and you look at the menu and there are 10 entrees, and you pick your favorite entree, but then your waiter says, "Oh, do you want soup or salad?" And also pick a side, and you check, and there are 5 side dishes, and you panic because you weren't ready for that. It was hard enough to pick the entree, and now the waiter's right there. You have to make all these decisions. It gets me every time. How many different options for a meal do you have? Yeah, good. So we've got a 3-step process. Step 1, pick an entree. Step 2, pick soup or salad. Step 3, pick one of the 5 side dishes. Rule of product says there's 10 times 2 times 5 different total meals you can end up with for 100 options. Okay. So let's do another example. Now, you go to a restaurant and you're trying to figure out something to order, and the menu has 5 pork dishes and 4 beef dishes and 6 chicken dishes and 3 veggie dishes. How many ways are there to order a dish now? Good. Meshvi gave me the answer I was hoping somebody would give me, which is, well, obviously if I'm going to a restaurant, I want one dish of every type. I'm going to order 1 pork dish, 1 beef dish, 1 chicken dish, and 1 veggie dish. To which I say, sounds like a good time, but most of us go and only order one thing. Sorry, don't want to shame you. You know, however you eat at a restaurant, totally fine. But what I'm getting at here is a different rule, not the rule of product. In this case, when I go to order a dish, I'm just going to pick one of these options. Either I will order a pork dish or I will order a beef dish, but I'm probably not going to order both unless I want a really big meal. So in addition to the rule of product, we have our rule of sum, ROS, which says instead of breaking things down into a process of steps, if we break things down up into a sequence of cases, so in order to count the number of something, that can be generated by two or more cases, instead of multiplying, we want to add together all of the different cases. So here, my total number of options is 5 options of pork dish, plus 4 options of beef dish, plus 6 options of chicken dish, plus 3 options of veggie dish, for a total of 18 options. So, okay, question from chat. It's not choice, right? We need to conclude on the basis of what possible things we can do. We can choose one from each. Yeah, okay, so we're getting at a good point in that when I'm writing these examples, I'm not really writing down the question. And in this case, I intentionally didn't write down the question because I wanted to mislead you. I wanted somebody to multiply these numbers together and then say, okay, but that's not what I meant. Obviously, no, maybe not obviously. Hopefully, obviously, when it comes time to ask you a question on a test or a quiz, we'll make the question very clear. A restaurant offers this many dishes. You're going to order one dish. How many ways are there to order your dinner? A restaurant offers 10 entrees. Every time you order an entree, you get a soup or a salad, and then you choose one of 5 side dishes. How many ways are there? Okay, now I'm multiplying. So we have these two tools, this rule of sum and rule of product, and it's going to be up to you to figure out how and when to use them. And how to combine them. So another example, this one not food. So suppose you want to play the lottery. And the way that this particular lottery works is you pick 6 numbers. Each number can be 1 through 69. And I want to know, given a particular lottery number, so they pick out the winning numbers. And let's say with repetition. So they've got the 6 different tumblers, and each one has all of the numbers 1 through 69. And they pick a number for each one. So at the end, they get 6 numbers, each of which can be any number 1 through 69. They pick the number for a given night. I want to know not just how many ways can you win, but how many ways can you match all or all but one of the winning numbers. So obviously, if you match all 6 numbers, you win the big jackpot. It's great. You're happy. Millions of dollars. But the way the lottery works, if you match 5 out of 6 of the numbers, you still win. Maybe not the huge jackpot, but you still win a whole bunch of money. How many ways can you have, let's say those are the only 2 ways to win. How many ways can you have a winning ticket? Got some good guesses. 70, 69. So let's think about it. Let's try and use our rule of sum, our rule of product. So first of all, we've got 2 different cases that we're dealing with. An important thing that I didn't put explicitly into the rule of sum, but these cases have to not overlap. Right? You don't want to count the same thing twice. So inherent in when I say cases. So we've got 2 different possibilities here. One possibility is that we match all numbers. Second possibility is that we match all but one. So how many ways are there to match all of the numbers? This one's not a trick question. Yep, just one. There's only one way to match all the numbers. Your first number has to be the first number, your second number has to be the second number, your third number has to be the third number, all the way down. But now let's think about how many ways are there to match all but one number. Suppose the winning number was, I don't know, 7, 13, 21, 56, and 9. 1, 2, 3, 4, 5, and 5 first. Forgot about that one. Okay, 5, 7, 13, 21, 56, and 9. That's the winning number. So there's only one way to win. You have to have picked exactly those numbers. But how many ways can we match 5 out of 6 of these numbers? So I've seen 69 a couple of times. Why 69? Where does 69 come from? Okay, so interesting. So how many options are there if I want to match all but one number? I see the argument, okay, well, matches, 69 options for the last one. But it actually can't be any number. Because if it's 9, then I didn't match all but one number. I specifically want one number to not match. So the number that doesn't match has to not match. It's not 69 options, it's only 68 options, because I have to pick something different. If I leave myself the ability to pick 9 for the last number, my cases overlap. Right? I might accidentally count the match all numbers twice. So counting is tricky, right? Already, we're just combining rule of sum, rule of product. There's one other thing going on, though, which maybe I wasn't clear enough about in my question. But if you've played the lottery, you know there's different ways of running it. And I actually don't play the lottery very often. But let's say that order matters. Let's say that if your ticket was 7, 5, 13, 21, 56, 9. Well, sorry, you don't win anything at all. Because 2 of your numbers don't match. And in this lottery, you have to match everything or all but one. Those are your only options. So now if order matters, there are 68 ways for your number to not match. But there's also 6 positions where the matching number can happen. So we've got a rule of product thing going on. Step 1, pick a position that doesn't match. 6 options for that. Step 2, pick a new number. It's got to be a new number, so we only have 68 options. So 6 options for your position, 68 options for your new number. Distinctly new, so 68, not 69. Rule of product, and I want to point out, right, we're already using this clause from rule of product that says it's just the number of options that doesn't matter. Because if I pick first position, then my 68 choices are anything but 5. But if I pick second position, my 68 choices are anything but 7. Different choices, but always 68. So I'm allowed to use rule of product. So 6 times 68 gives me 408. And now I can use rule of sum to add my disjoint cases together and get 409 winning tickets. And again, that's assuming that order matters. Things get a lot messier if order doesn't matter. Worth pointing out. Any questions on that example before we go on? Yeah. So we want to generate a ticket. It's a winning ticket. It matches every number except for 1. So we're going to generate our ticket with a 2-step process. Step 1 is choose which number it is that does not match. Right? So we're matching 5 out of 6. That means 1 out of 6 is not matching. So we're picking one of our 6 positions. Position 1, position 2, position 3, position 4, position 5, position 6. One of those options. And then, once we've fixed our position, we pick a new number to go into that position. So maybe I pick position 3, and then I pick the new number 36. So the new lottery card that I'm generating is 5, 7, 36, 21, 56, and 9. That's my 2-step process. Step 1 was pick a position. Step 2 was pick a new number. So the rule of product says if I can break things down into a process of steps, I multiply the number of options of each step. The step where I choose a position had 6 options. The step where I choose a new number had 68 options, not 69, because it has to be a new number. Rule of product says multiply those 2 things together. 6 options, step 1. 68 options, step 2. 6 times 68 gives me 408. Okay. Back to food. Why is it 408 plus 1 winning tickets? That is our rule of sum. So remember that there's 2 ways to win. 2 different cases where you win. One case where you match all the numbers. one case where you match every number but one. Those are two different cases. Rule of sum says to add them together. You already fixed one position, then y6. Because when we fixed our position, we had 6 different options for that position. Right? You win by matching all but one of the numbers. But I didn't tell you which number it is. So if I list all of the winning tickets, I could list all of the tickets where position 1 is different. Then I could list all of the winning tickets where position 2 is different. Then I can list all of the winning tickets where position 3 is different, position 4, position 5, position 6. Yes, if there was a different lottery. If it wasn't, you just have to match all but one. If it was more specifically, you have to match all or all but the last number. Then you would only have 6 to 8 options, because it would be only this 9 that you are allowed to change. But here I'm allowed to change any one of these numbers. Okay. Okay, back to food. So I actually went and looked this up. There's a Winnipeg pizza chain called Pizza Pizza. And Pizza Pizza offers 37 different toppings. At least on their website. How many different pizzas can you order from Pizza Pizza? Give you a second to think about this one. A lot. I agree, Larry. Larry's got the right answer. Yep, you're able to put on all the toppings. Not quite 37 factorial. It's a little bit too big. It is a big number, though. So let's think about it. Let's think about it in terms of rule of sum and rule of product. What's our process going to be? This is a tricky one, by the way. We're just using rule of sum, rule of product. How can we use those rules to come up with a plan for counting all of these? Yeah, there we go. Got two different paths here. Two different paths, and I like it a lot. I want to talk about both paths. Because before we start doing this problem, we're not going to know which one of these paths is better. So let's go path 1. We're going to start by breaking into cases. How many toppings do we want? And then path 2, we're going to consider for each topping, do we want it or not? Okay, so if we go down path 1, we're breaking it up into a bunch of different options, right? So we're going to be using our rule of sum. So we could have 1 topping, 2 toppings, 3 toppings, all the way down to 18 toppings. And I'm missing a case here. What's the case that I'm missing? Zero toppings, also worth considering. Okay, let's see if we can fill in some of these. How many ways are there to make a 0 topping pizza? 1 way. How many ways are there to make a 1 topping pizza? 37. 37 different options. How many ways are there to make a 2 topping pizza? Good. So we want to come up with, oh, sorry, why up to 18 toppings? Correct. Because there are 18 veggie toppings. So in my notes, I had it going up to 18, but then I realized there are more. Totally correct. Should go all the way up to 37. Sorry about that. Are you allowed to use a topping more than once? Really important question. No, we're gonna outlaw double toppings here. We're just gonna say the type of toppings on a pizza is what defines the pizza. Yeah, so let's go all the way up to 37. Okay, so now 2 toppings. I want to pick a topping 1 and pick a topping 2. So it seems like I want 37 times 36. But there's actually a problem with 37 times 36. And it's subtle. The subtle problem with 37 times 36 is if I'm following this process, I can accidentally count the same pizza twice. And because I want to make half of you upset, 37 times 36 means first I pick pineapple, then I pick ham. A separate time, first I pick ham, then I pick pineapple. Oh, but wait, that's actually the same pizza. I picked the same combination of toppings more than once. I'm double counting ham and pineapple pizza. Because the order I put toppings on doesn't matter. So in order to go down this path, this totally works, but in order to go down this path, we're going to need a new idea. And also, we're going to have to add up 38 different numbers, some of which might get super complicated. So path 1 works, but let's look at path 2 and see if it's better. So path 2, separate way of thinking about this. Instead of our top level question being how many toppings do we want, we're going to ask ourselves, okay, let's look at the list of toppings. Topping number 1, arugula. Do we want arugula on our pizza? Right? This is the mom friend of the group. We're ordering pizza. We've all had a great night of drinking root beer. And now it's time to order a pizza. And mom is like, okay, do we want arugula? Yes, no. And then we go on to second question. Do we want, I didn't remember what was second. Do we want anchovies? Yes, no. And we're just going to go down this list, 37 different toppings, and for each one, ask yes or no. So this is a rule of product calculation. We have 37 steps. In each step, we have 2 options, yes or no. So arugula, yes, no. Anchovies, yes, no. We're going down the whole list. It's going to take us a long time. For each one, we decide yes or no. At the end, we come out with a pizza. We come out with some toppings. So rule of product says we multiply each one of these together. 2 options for step 1, 2 options for step 2, 2 options for step 3, all the way down to 2 to the 37 pizzas. What is 2 to the 37? How big is that? Don't know exactly. Here's a tip for the computer scientists among you, though. We can estimate this by saying two to the 37 is equal to 1 over 2 cubed times 2 to the 40. Right, just canceling out 3 powers of 2. This is 1/8 of 2 to the 10 to the 4. So far, everything's equal. And here's where the estimation part comes in. This is approximately equal to 1/8. 2 to the 10 is 1,024. So approximately 1,000 to the 4th power. 1,000 to the 4th power. So 1,000 is to the 1st power. Squared is 1,000,000. Times another 1,000 is 1,000,000,000. Times another 1,000 is 1,000,000,000,000. So this is approximately 1/8 of 1,000,000,000,000, or approximately 125 billion different pizzas. Okay, some questions in chat to talk about. Do we need to add the no topping pizza? Very important question. Is it already included? How do we get to the no topping pizza? We have to make sure that our process, our rule of product process, can generate the no topping pizza. How do we generate it? Well, we go through each step one at a time. Arugula, yes or no? Not feeling arugula. Let's go no. Anchovies, yes or no? Nah, no anchovies. No. We go down the list. If we choose no every time, we end up at the pizza that has no toppings. So the no topping pizza is one of our options. Just like the all topping pizza, the 37 different toppings, also on there. We've got arugula, yep, we love that. Add it on. Anchovies, pile them high. Pepperoni, feta cheese, it's all on there. How did we get here? So this estimate part, or the 2 to the 37? Not sure exactly where the here we got is. How do we get to the 2 to the 37? Okay, so we're doing our rule of product calculation. Rule of product calculation say break the thing you're counting down into steps. So I'm listing out a 37-step process. Then once you have your steps, count up how many options there are in each step and multiply all of those numbers together. So for step 1, I have 2 options, arugula, yes or no. For step 2, I also have 2 options, anchovies, yes or no. Each one of these 37 steps, I've got 2 options. So at the end, I multiply 2 times 2 times 2 times 2 times 2 times 2, 37 times. That's what gets me the 2 to the 37. Is the estimate part required? No, absolutely not. This can go off in the bonus content box. That's a little freebie. Estimating powers of 2 is a useful skill that if you're a computer scientist, you're really going to want to be able to do. Also, if you're a mathematician, frequently useful. But computer science comes up all the time. We want the answer in this class, 2 to the 37 pizzas. Since you don't have a calculator, you should not be able to find the exact answer. But, you know, if you're being interviewed by the local news and they want to know how many pizzas there are, well, saying 2 to the 37 is, they're going to be like, what's that? So you need to be able to come up with an estimate. This estimate is about 125 billion. Which means, for sure, there are pizzas that no Canadian has ever ordered. Because there's no way Canadians have eaten 125 billion pizzas. Challenge accepted. For path 1, can we eliminate that? Yes, we're going to get to that. There is a way to do path 1. Path 1 is never the fastest way. But there is a way to make it happen. We just need new ideas. Haven't gotten there yet. We will get there. But I do want to mention one thing here. Abstract a little bit away from our pizzas. What are we really doing in this pizza example? We're really choosing a subset of the pizza toppings. So the boring math way to ask the same question is, how many subsets of a set A exist? Or another way of asking this question, what is the cardinality of the power set of A? Same question we just asked, now in a boring math context instead of talking about pizza. Exactly right. We can do the same rule of product strategy. We list out the elements of A, and for each element, we ask, do we include this element? Yes or no? Do we include this element? Yes or no? Do we include this element? Yes or no? For a total of 2 to the A, 2 to the cardinality of A elements. The number of subsets, the size of the power set is 2 to the A. So we looked, at one point we looked at the set 1, 2, 3, and we looked at how many subsets there were here, or we looked at the subsets. We now know that there will be 2 cubed, 8 different subsets. Right, and those were the empty set, the set containing 1, the set containing 2, the set containing 3, the set containing 1 and 2, the set containing 2 and 3, the set containing 1 and 3, and then the set containing all 3 of them. These were our 8 options for a subset of this set. So this was the power set, these 8 things. Okay. Now let's get to what some of you wanted to get to earlier, which is how many ways are there to shuffle a deck of cards? So 52 cards. You've taken out the jokers. We've just got our regular 52 card deck. We shuffle it up. How many outcomes do we have? So let's think about this in terms of a rule of product calculation. Which card is first? Pick one card to be first. How many ways are there for a card to be first? Pick from 52 cards. Good. This is first card. Okay. How many options do we have when it comes time to pick our second card? we only have 51. Our first card has already been picked. There's only 51 cards left now. How many for our third card? We're down to 50. And here, we don't have that problem we had before, because order does matter, right? Picking ace of spades to be first and two of clubs to be second is different than two of clubs first, ace of spades second. So if we keep doing this, we're going to have a 52-step process. But we don't have the same number of steps. We don't have the same number of options at each step. The number of options is constantly changing. First we have 52, then we have 51, then we have 50, then we have 49. How many options are we going to have for our 52nd step? Our 52nd card, our last card, how many options are there? Just one. We'll only have one card left over. So the number of ways to shuffle a 52-card deck is 52 times 51 times 50 times 49, all the way down to 1. And as we've mentioned, we have a special name for this. This is 52 factorial. This exclamation point is pronounced factorial. So let's define that formally. We have n factorial is a function. 0 factorial is equal to 1. And n factorial is equal to n times n minus 1 factorial for n greater than or equal to 1. So this is a recursive formula. And our recursive formula says, if you want to know n factorial, you multiply n by n minus 1 factorial. And you just keep going until you get down to 1. So 52 factorial is 52 times 51 times 50 times 49 times 48, all the way down. We could also write this in terms of capital pi. So I'll say alternatively, n factorial is equal to the product from I equals 1 up to n of I. Very good. If we just wanted one specific card, that is a different question. Okay, so factorial, fun little aside. My mother is an English major. My father is a physics major. Was, I guess. They're not still in college. And they met in high school. So they were both working on college homework together. And my mother was taking a math class. And my father's studying or whatever, and she interrupts him and she goes, "Honey, what's 6?" And he goes, "What?" She goes, "It's in my math homework. What's 6?" Just like really excited. And he's like, "What are you talking about?" And comes over and looks, and she was asking, what is 6 factorial? But when you're an English major, this is an exclamation point. It just means be really excited about what you're saying. So she pronounced this 6. But 6 factorial, you don't have to be super excited when you tell it. Love that story. Love my parents. Anyway, okay, so factorials, they help us count these things. The things that they help us count, this number of ways to shuffle a deck of cards, has a fancy math-sounding name. It is a permutation. So a permutation of a set is an ordered arrangement of its elements. So we put the elements of a set in an order. That's a permutation. In this case, we can think of putting the cards of the deck in an order. That's what shuffling is. So the set of cards might be something like Ace of Hearts, Two of Spades, which are harder to draw, and King of Diamonds. Let's just say I have those three cards. That is a set of cards, but a permutation is a specific ordering of the cards. Maybe I have my three cards lined up, and I have Ace of Hearts in the middle, and Two of Spades on the bottom. This is to be envisioned as being read from top to bottom. King of Diamonds on top. Right, so specific ordering. And the number of permutations of a set with n elements is n factorial. Okay. One more fun math joke for you. You may have seen these viral internet things. 99% of people can't do this or whatever. What is 230 minus 220 times 0.5? You might not believe it, but the answer is 5. So this is my favorite one because the level 0 is people say 230 minus 220, I get 10, times 0.5 gives me 5. And then the level 1 goes, but you don't know order of operations. Order of operations is do multiplication first. 220 times 0.5 gives me 110. 230 minus 110 actually gives me 120. But that's when we get to level 2. That's what I said. I told you the answer is 120. Because 5, I didn't say the answer was 5. I said it was 5 factorial, which is 5 times 4 times 3 times 2 times 1, which is 5 times 4 is 20. 3 times 2 times 1 is 6. It's 120. So, you may not believe it, but the answer is 5. I just forgot the period at the end of my sentence, you see. Yeah, so this is the classic math teacher nightmare, because this question you can get right for the wrong reason. Okay, I've got a lot more examples today. We didn't do a break yet. Let's do this. Let's keep pushing forward for another 15 minutes, and then we'll end 5 minutes early today. Just to give everybody a breather. I think we just got some momentum going, so rather than give you that break, let's just keep going here. So I want to ask another question. Let's say we have 10 athletes competing. When I wrote this lecture, it was during the Olympics, but the Olympics are over now, so it feels a little dated. But we've got 10 athletes, and only first, second, and third get medals. And they're different medals. They're gold, silver, bronze. How many different podiums are there? How many different ways are there to have a first place, a second place, and a third place? Yeah, good. We've got 10 times 9 times 8, giving us 720 different podiums. And this is our rule of product again. First, choose a first. And we have 10 ways of doing that. Second, we choose a second place. And now we can't re-choose the first place athlete. They're already first. So we have 9 people left over for second place. And then third, we choose a third place finisher. 8 options left over for that. Multiply them together, 10 times 9 times 8. So what we're doing here is sort of a permutation, but we're not rearranging all 10 athletes. We're only choosing 3 of them. And what are we doing in this case? We're stopping our permutation calculation early. We're doing 10 times 9 times 8, but we're not doing 10 factorial because we don't keep going. There's no 7, 6, 5, 4, 3, 2, 1. We stop here, just 10 times 9 times 8. So this is a permutation of size R. Permuting R elements from a set of size n. How many ways are there to do this? Exactly right. Really good, Owen. We're going to say we want n times n minus 1 times n minus 2. We want to multiply together r things in total. So we have start with minus 0, minus 1, minus 2. In order to get r things total, we're going to go to n minus r plus 1. That's the last thing we multiply. So here we'll multiply, or blah, blah. Here we are multiplying 3 things. So 10 times 9 times 8. The last thing is 10 minus 3 is 7 plus 1. So we stop at 8. And a better way of writing this formula, this really clever idea, is I want to do n factorial divided by n minus r factorial. Why is this what I want to do? This n minus r factorial cancels out all the stuff I don't want from my n factorial. This is, if I look at my specific example, if I look at 10 factorial divided by 3 factorial, divided by 7 factorial, this is equal to 10 factorial over 10 minus 3 factorial. That's what I'm working with. This is going to give me 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And this is going to give me 7 times 6 times 5 times 4 times 3 times 2 times 1. And I can cancel out all of these factors until all that I'm left with is 10 times 9 times 8. So it's true that we could also write this in the form product I equals 8 up to 10 of I. This means the same thing. But this is going to be our preferred way of thinking about it. This is the answer that we'll expect to see on a test or a quiz most of the time. Yeah, so I also see in the chat something like this. This is something you may have seen in a previous class or in high school. We're going to not use this in this class. We prefer the formula version. 10 factorial over 7 factorial. So this will not be accepted, or I should say may not be accepted. Individual graders might end up accepting it, but can't promise you that that'll be accepted, so don't use it. Okay. So if we want to choose our elements from a set of size n, we've got this permutation of r elements, n factorial over n minus r factorial. Another type of permutation I want to mention is when elements are not unique. So how many ways are there to rearrange the letters in the name Anna? Can we arrange the letters in the name Anna? So Anna has 4 letters in it. Our first thought might be 4 factorial. But if we try listing them all out, we can't quite get all the way up to 4 factorial. So A-A-N-N, A-N-A-N, A-N-N-A, N-N-A-A, N-A-N-A, N-A-A-N. My favorite one is last. I think that is all of the different ways that we can rearrange the letters of Anna. So this is only 6. 4 factorial would be 24. So something's going on here. I'm missing some. And the thing that I'm missing is that the two A's and the two N's are the same. So every time I'm looking at one of these, each one of these secretly corresponds to 4 different options. If I gave my letters individual names, A1, N1, N2, and A2, if I look at one of my arrangements, non, there are 4 different arrangements that all give me non. I can have write it 4 times first. I could have non with 1, 1, 2, 2. But I could also have it with 1, 2, 1, 2. Or with 2, 1, 2, 1. Or with 2, 2, 1, 1. All of these are different ways to rearrange these letters if I named them, but they all give me the same final arrangement, NAAN. So in order to combat this, in order to cancel out the duplicates, I need to figure out what's going on. What's going on here is that any arrangement of this, I can shuffle the ends, I can swap the ends, or I can swap the A's. So that's why each one of these arrangements accounts for 4 different orderings of these letters. So as was mentioned in chat, the total number of ways to actually arrange this is not 4 factorial. It's 4 factorial to arrange all the letters, divided by 2 factorial, because there are 2 A's, times 2 factorial, because there are 2 N's. And every time I rearrange the letters, the ordering of the A's doesn't matter, and the ordering of the N's doesn't matter. So this gives me 4 factorial over 4. That's 24 over 4 is 6. So I found all 6 of my different arrangements. So let me give you an example for that one. How many different ways can we rearrange banana? Good. Seeing some good answers in chat. So in banana, I have 6 letters, which gives me a 6 factorial. But any time I take a permutation of those 6 letters, I don't actually care about the order that the 3 A's are in. I don't actually care about the order that the 2 N's are in. And there's just one B, but for completeness, I can write this. So I'm perfectly happy with this as an answer. But we could also calculate what this is. 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 times 2 times 1 times 1. We can do some cancellation. 3 and 2 together take out a 6. 2 can take out a 2. And the 1s don't really matter. So 5 times 4 times 3 looks like 60. That's what I'm getting. Yeah, and so it is worth noting that this number is equal to 6 factorial over 3 factorial, 2 factorial. And so this answer, I think, is perfectly fine. This answer shows slightly more understanding. It just tells a better story. But there's nothing wrong with this answer. I would expect this answer to receive full credit. I just like this answer better because we can see that all 6 letters are accounted for. Everything adds up to 6 in the right way. When are you to use factorial or permutation? When they are appropriate, when they help you solve the question. So a factorial is a number. A permutation is a thing. A permutation describes an arranging of a set. The number of ways to come up with a permutation is n factorial. So I wouldn't say that an arrangement, I wouldn't say that this is a factorial. I'd say that this is a permutation. But in talking about how many of them there are, I use factorials to describe that number. Okay, so like I said, we didn't do a break today. I sort of plowed right through, so I will stop here. I'm happy to keep answering questions, but that's the end of today's lecture. I'll see anybody who wants to hang out during office hours. Oh, good question in chat. The 52 card example is 52 factorial. In this case, there's really, each card is individual, so it would be 52 factorial over 1 factorial times 1 factorial times 1 factorial times 1 factorial 52 times. But actually, in this case, I really just like thinking of it as a permutation. And so permutation of distinct elements, just 52 factorial is fine. What a good question.
I have a question about the 10 athletes.
About which
so
one?
So you said 10 athletes problem.
Oh, 10 athletes, sure. Yep.
So you said it uses the rule of, right?
Sorry, you cut out there. It uses what, sorry? Just, I can't hear you well.
Hear me now.
Just heard the very end of that.
Is it clearer now?
Yes, now I can hear you well. Yep.
Okay. Yeah. So you said it uses rule of products, but the rule of products, like the definition you gave, says the number of options of each step is the same regardless of previous choices. But for this case, the first, like the ways of picking the first person is 10, but the ways of picking the second person, doesn't that change because we've picked a person from the previous, like because of the previous step?
Yeah, so this is really good. The specific people you have to choose from changes, right? If Robert and Dan are 2 of your athletes, if Robert wins, then when you go to choose second place, you've got Dan and 8 other people. But if Dan wins, then you've got Robert and 8 other people. But no matter what your choices are, there are always 9 of them. You've got 1 winner, which means there are 9 people left that you can choose from for second place. Who those specific 9 people are changes, but that there are 9 of them, that's fixed. And so that's what we need for rule of product. As long as there's always 9, then we're good.
Okay.
But yeah, really good question. All right, I will stop the recording here.